our senses. How do we perceive? How do we sense things? How do I know, for instance, that this is red, that this is blue? How, if I'm going over here and playing a cheap game of cornhole, how do I know how far away the holes are? Okay? What affects my behavior? What affects how well I can see the hole, how I can roll the back? How does that work? It's all sensation and perception. What is sensation and perception? Well, sensation is the taking in of information. Taking in, for instance, the wavelength of the light. Taking in the sounds of the birds chirping on this relatively beautiful day. Me taking in the fact that my hair is blowing because it's decently windy out. Sensation is the taking in of the information. Perception is the idea of what does that information mean. It's interpreting that information. It's interpreting this as blue. It's interpreting the sounds that you hear as birds chirping. That is perception. I am perceiving birds chirping. I am perceiving the color blue. So that's sensation and perception. Well, there's a bunch of things that come along with that. Some of the main terms are, first of all, we have absolute and difference threshold. How much light does it take, for instance, to see the shirt? How much light does it take to see the things like the cornhole beanbags? Absolute threshold is the minimum amount of stimulus necessary to detect it. So the minimum amount of light waves necessary to detect that there's light. That's absolute, to detect it 50% of the time. That's absolute threshold. Okay? So it's something like just like a candle a certain amount of away. Absolute threshold, the minimum amount to detect it 50% of the time. Difference threshold is the minimum amount to detect a difference 50% of the time. Now, the minimum difference can vary depending on what the starting place is. So, for instance, if it's really quiet, then all I have to do is raise my voice a little bit and you detect a difference. If it's really loud, if you're at a party, somebody would have to change something considerably in order to detect a difference. That's Weber's law. Weber's law is that the amount of difference needed to detect a difference depends on the initial stimulus. And difference threshold is the amount needed, the amount of change needed to detect a difference at least 50% of the time. So more than chance. So that's absolute threshold and difference threshold. We have this thing also, if you're thinking about other things that affect how you're sensing and perceiving things. One thing is sensory adaptation. I'm sitting here and in the yard and it was recently mulched. When we first mulched, what does mulch smell like? It has a particular smell. When you first open up the vehicle and there's the bags of mulch in it, you notice the smell. After a while, after you've been working with it and lugging the bags of mulch around, you don't seem to notice the smell as much. That's an example of sensory adaptation. Your senses get used to a certain smell. You see this in a number of things. You see this in the summertime when you jump into a swimming pool. When you first jump in, it seems really cold. But then you get used to it and you don't notice the coldness as much. If you're in a house where people smoke, you may notice the smoke at the very beginning, but after a while you don't notice it. It can happen the other way too. It can happen if you're in a theater in the middle of a day and your eyes are adapted to the dark and you go out, boom, it seems really bright. So most of the time sensory adaptation is you get used to it and you don't notice it. But it can be the opposite, that you get used to something and then when there's a change, you notice it big time. That's sensory adaptation. So what else affects perception? Attitude. I can perceive cornhole bags better if I like the game. That's attitude. If I have experience with it. They've done some studies looking at chess players. And people that have experience with chess perceive the board differently than people who don't. They're thinking about it differently. They're perceiving it differently. So that's your attitude, your experience, your motivation. If I'm really motivated to beat somebody in cornhole, I'm going to have a different perception. I'm going to be say, well, is it close enough? Is it halfway in? There's a lot of different things it affects your attitude, your motivation, your attention. The fact that I'm not really, that right now I decided, I'm going to listen to see if there's any birds chirping. I perceived it because I decided to pay attention to it. So you have your attention, your attitude, your motivation, a lot of different things. Your cultural experiences can affect your perception. Cultural experiences and general life experiences. Like I said, people who have experience playing chess are going to perceive a chessboard differently. People who are watching a soccer game, those who know how to play soccer are going to perceive it differently than people who don't. Same thing with football or other sports. Music, those who are experienced musicians are going to. So your background, which includes your culture. Okay? So those things affect perception. The last thing in terms of just general perception stuff is subliminal perception. Have you all heard the stories of back in drive-in movies? They would have these things. It's like they would have it blink real fast. Get food, get drink, and they would hope that it would make you go buy stuff. You wouldn't know that it flashed on the screen. It would be too quick. But that was subliminal perception. Well, does subliminal perception work? Do we really perceive things that we aren't consciously aware that we're perceiving? Sort of. Yes, we perceive things that we're not consciously aware of. Does it make us do stuff? Not necessarily. There's been some studies looking at the effects of subliminal perception. Subliminal perception, things that are slightly below our conscious awareness, can have some effect on our emotions and some effect on our specifically emotional perceptions about things. But it's not the be-all and end-all, and it's not like you're not putting somebody on autopilot and turning them into a robot that's going to be like, I will buy that car, that kind of thing. That's not how it works. It can slightly affect our attitude, slightly affect our emotional perception of something. But that's it. So subliminal perception. Those are the general things. Let's move on to specific senses. We have eyes. We have vision. So we have vision, hearing, the chemical senses, taste and smell, and then the sense of balance and things like that. So let's start with vision. Vision is a function of light coming into the eye. Well, what exactly is light? Light is in waves, and you have a wave of light. You have how tall the wave is, which is amplitude. You have how far apart it is, which is wavelength, and that is also frequency, because waves that are smaller come more often. So frequency and wavelength, this just describes how long each wave is. Frequency describes how often they come, but they are directly related because longer waves come less often. So, what does that tell you? Well, the amplitude or height tells you the brightness of a color. This is a bright blue. Okay? That would be a really high, pretty high wavelength of light. A pretty high amplitude. Wavelength or frequency tells you what color it is. It doesn't tell you the brightness. It tells you that is blue. This is red. Now, if you look, you all have heard of the electromagnetic spectrum, the spectrum of waves, and that there's only a portion of it which is visible light. Within that portion, there are different wavelengths, frequencies, and that's what determines hue or color. So how fast they come, which is also how long the waves are, determines color. So we have the amplitude determines brightness, the wavelength or frequency determines color, and the other thing is what's called saturation. And that's, do you have a bunch of waves that are all the same? Are they all in sync? Or do you have some scatter? That's what tells you what kind of color you're getting. This is a very saturated color. It is a blue. All the wavelengths coming off my shirt are blue. You have other colors which are a little more muted. The grass behind me is green, but it's not a bright green. It has some other colors in it. The sky is kind of cloudy. So it's not a blue. It's more muddled. Saturation, that is the idea of saturation. Saturation are the wavelengths all the same, and thus they will make a really true color, or are they kind of muddled? Is there a variation in wavelength, and it's going to give you a color that's not quite as true? Okay, it's not going to be a blue. So that's how wavelengths work. Okay, so how does vision work? You have light coming into your eye, and it comes in through the pupil, which is the black center, the hole. Okay, you have the iris is the colored part of your eye, and the iris is a muscle that expands and contracts to let light in. Light comes in through the pupil. Okay, it goes through the cornea, then goes through the pupil, then goes through the lens. The lens, think of an eyeglass lens. The lens is a part of your eye that is bendable. Now, we'll find out that it gets less bendable with age. So the light waves the lens works on them to bend them so that they hit the back of your eye, which is the retina. Okay? The retina is the part that has the photoreceptors, or the rods and cones. Now, the rods are more on the peripheral. The cones are more in the center. You will notice, if I hold this up to the side of my face, I would not necessarily see that it is red. I did this experiment in class where I gave students Jolly Ranchers and told them, don't look at the color, hold it up to the side of your face. And they had trouble figuring out what color it was. The one that people did really good on was the grape, because it was dark. So you can see that's because on the outsides of your eyes, you have more rods, which help with your peripheral vision, but they're mostly black and white. The photoreceptors responsible for color are your cones, and they're more in the center of your eye. So, hits the rods and cones. The rods and cones do what's called transduction, which is take that physical energy and change it into a neural impulse. Take that wavelength and change it into a neural impulse. That's transduction. Okay? And you'll find that with all the senses. Transduction is that changing of that physical input into a neural impulse. So the rods and cones send an impulse to the bipolar and ganglion cells, which send an impulse through the optic nerve, which crosses at the optic chiasm. So this eye gets picked up on this part of the brain. This eye gets picked up on this part of the brain. It crosses at the optic chiasm. Then it goes through parts of the eye, through the occipital lobe. Also gets processed a little bit in the frontal lobe in terms of organizing and processing what it is, but the occipital lobe is the main part for vision. So that is how vision works. Okay. The next question is, how do we see specifically color and depth? Well, color, there are two theories. There's the trichromatic theory, which means we have 3 different types of cones. And all color is made up of 3 different types of cones. This would mean that just the red cones were firing, and that's how I would perceive it as red. So what is trichromatic is that color is all perceived because of whatever mix of the 3 different cone types are triggered. That's the trichromatic theory. Well, then you had some people come up and say, that can't explain it all, because it doesn't explain people who are colorblind and people who are only colorblind red-green, for instance. It doesn't explain what's called after images. There's a classic thing that has an American flag that is green and orange and black. And if you stare at it and then take it away and put a white piece of paper, you'll see a red, white, and blue American flag. That's an after image. And that trichromatic theory didn't explain after images. So they came up with what was called the opponent process theory, which is instead of just 3 cones, we have receptors that are red, green, black, white. Okay? We have receptors that are almost like seesaws, that if you trigger, for instance, if you trigger the red one and you keep triggering it, then when you stop, it's going to whoop and start making green. That's the after image. Because on the flag, on the different colored flag, it's green, and when you take off the green, you're going to see red. So that's the after image. So that explains it. In reality, we have both. We do have 3 different types of cones. So when you're talking about cones, it's the trichromatic theory. When you get further in the bipolar ganglion cells, when you get further in, we have cells that work more on the opponent process theory. So it's a combo. That's color vision. Then we have depth perception. How do I know? We did the cornhole, okay? We did the cornhole, and how do I know how far away that thing is? And I just missed. How do I know how far away that thing is? Depth perception. How do I know how far away the camera is from what I'm looking at here? Depth perception. How does that work? Well, we have both monocular and binocular cues to depth perception. Monocular, one eye. I can cover an eye, and I can cover one of my eyes and see how far something is away. I don't need both eyes to do that, because I see, for instance, that one thing is overlapping with another. So we have overlap. I see texture gradient, which is the things that are farther are fuzzier. Linear perspective. If you're going down a road, the lines seem to get closer together. And the closer together they are, you interpret that as farther away. So we have overlap, linear perspective, shadowing. I see shadows on different things, and it tells me how far away they are. Those are some monocular cues to depth perception. Binocular is using both eyes. So, I can compare the images that I'm getting in both eyes to see where it is in space. Is it over here or over here? It helps me see that. When the light waves hit each eye, how close my eyes need to move into each other, convergence. If I go like this, the closer I get to my nose, the more my eyes are going in. That's convergence. Those are some binocular cues. So, how do we see depth? We see depth through monocular cues like shadows and overlapping and linear perspective. We see depth through binocular cues like convergence. So that's depth perception. That's pretty much vision. But vision is not our only sense, right? We have vision and we have hearing. Right now, I can hear birds chirping. So how does that work? How do I hear that? Well, hearing is also based on waves, sound waves. Just like the height of light waves tells you brightness, the height of sound waves tells you loudness. Okay? The frequency or wavelength tells you pitch. It tells you, is it really high or is it really low? It tells you pitch. So the frequency tells you frequency or wavelength tells you pitch. Amplitude or height tells you loudness. And saturate, like whether it's all the same or whether there's different waves mixed in, what's called timbre. And those of you who are into music would understand that. It's the difference between if you have a middle C and you're playing it on a piano versus a violin, it's going to sound different. If I sing the same note as somebody else and it's the same note, our voices are going to sound slightly different. That's because of the mix of waves, and that's called timbre, and that's the way saturation works with sound. So you have waves, and you have the same thing as light. It just means different things. In other words, you have height, wavelength, and saturation. Height tells you loudness, wavelength or frequency tells you pitch, and saturation says timbre. So that's the waves. So how does that work? You have waves, sound waves coming into your ears, and the sound waves come into your ear canal, or what's called your pinna, and they bounce on the eardrum. Well, your eardrum vibrates. Your eardrum vibrates and knocks three little bones, ossicles, the hammer, anvil, and stirrup. And those little bones move, and those little bones eventually knock on what's called the oval window, which is another membrane that vibrates. The oval window vibrates, and it vibrates a fluid in the cochlea of your ear, and that fluid triggers little hair cells on the basilar membrane in the cochlea, and those hair cells are the receptors. They are the cells that do the transduction, that translate the waves actually into a neural impulse. So, sound comes in, goes through your ear canal, hits your eardrum, vibrates the bones. The bones vibrate the oval window. The oval window starts moving the liquid in the cochlea. The cochlea, that liquid, moves those hair cells, and those hair cells trigger an action potential, and they trigger an impulse down the auditory nerve, and it goes to the temporal lobe of the brain, eventually to get processed. That is hearing. That is sound. In terms of comprehension, so that is sensation. In terms of perception, we also have, remember we talked about Broca's area and Wernicke's area in terms of language perception. Understanding you're getting the impulse from what I'm saying right now. But there's a difference between sensing the pitch of the voice and perceiving the words. So Broca's and Wernicke's are more production, again, the production and interpretation of speech. So basically, we have the parts of the ear and hearing. We have pitch perception. Just like in color vision, there are two different theories of pitch perception. There's place theory and frequency theory. Frequency theory is how fast the waves are coming in, how fast / wavelength, because the length of the waves, the longer the waves, the slower they go by. That is one theory, that solely determines pitch. Well, sometimes it does. when you get so fast that it can't keep up with it, basically. You also have place theory, which is where, in other words, which hair cells are triggered on the basilar membrane. So it's mostly, you can say frequency equals pitch. And for a lot of cases, it's true. But there are certain circumstances where it's also the location on the basilar membrane that triggers frequency. Now, there's a couple other things before we leave sound. One is sound localization. If I hear a bird, how do I know where it is? Just like depth, think of this as the hearing equivalent of depth perception. How do I know where that sound is? Well, I can look at binaural cues, okay? Just like binocular cues, binaural cues. I can hear, when does the sound hit this ear versus this ear? And that tells me how far it is away. I can see, so I can use my other senses to determine where it's coming from. I hear a bird and I can look around for the bird. So there's a lot of different ways that I can do that. The time that it enters this ear from this ear, the loudness difference between the two ears, that can help localize sounds. The last thing is hearing loss. There are many different types of hearing. There are different types of hearing loss. There is temporary hearing loss, like for instance, you have an ear infection or you have allergies and you're all stopped up. And that middle part of your ear that has the bones is stuffed up. You have some hearing loss. Okay, you take antihistamines, you take antibiotics, you get it cleared up, everything's moving again. So it can be things like that, or it can be you have wax in your ear, you've gone swimming, and you have stuffed up ears because you've gone swimming. So there can be really minor things like that. Then there can be hearing loss in terms of, well, that part of your ear with the bones is not just stuffed up, it is messed up. There's something wrong with it. The little bones are not working right. Or your eardrum is not working right. Or the oval window is not working right. There could be problems all along the way. Another common form of hearing loss, or hearing loss that is one of the hard, like hearing loss that you see quite a bit, but it's not treatable in terms of you can't do much to make things normal, but you can do stuff to help people hear, if that makes sense, is having problems in the cochlea, having problems with those receptors. Really, if you have problems in that part of the ear, there's a couple different options. At an extreme level are cochlear implants. And that's what some people who have significant hearing loss end up doing, cochlear implants. The other is hearing aids. And nowadays, hearing aids are a lot more expensive than glasses, but they kind of work the same way. They modify the sound coming in so that it makes it easier to hear. They modify, you have a hearing aid prescription, and they modify different, they make certain pitches louder, the pitches that you have trouble hearing. So basically hearing aids. There's this whole thing in terms of, when you're talking about hearing loss, you have the idea of hearing aids and what causes people to have to get hearing aids. And then you have the deaf community and this question of, if you have a child who is deaf, what's the best way to deal with that? Some would argue one of the best things you can do is teach them how to speak and lip read, because, quote, they're going to have to they're going to have to survive in a hearing world, so give them the tools necessary to do that. Other people would argue that it alienates them from the deaf community, that ASL is a language, and it's important for them to learn that language and speak that language and be part of that community. So there's kind of arguments in both ways, and I'm guessing that a number of people would advocate for both in terms of being able to be a part of the community and learning sign, but also having some skills in lip reading and speaking so that when that's not available, then it's also an option, if that makes sense. But there are lots of opinions on the matter. So that's hearing loss. So we talked about vision, we talked about hearing. What about the other senses? We have chemical senses, taste and smell. Taste. We have sweet, sour, salty, bitter, and we have a new one, umami, which is kind of like a, is originally found in Japan, but think of it as earthy and savory. Those are different types of taste buds. Basically, you have chemicals coming into your mouth, your saliva you have food coming into your mouth, your saliva breaks it down, and those chemicals get picked up by your taste buds. And the taste buds are the receptors that do the transduction, that translate those chemicals into a neural impulse. So, those chemicals go to your brain and get interpreted as taste. Smell, similar way. You have odor molecules coming into your nose. You have little receptors in the top of your nose that pick up those odor molecules and interpret them as smells. Works in a similar fashion. This is the big question. Can you taste if you can't smell? There are people that have issues with taste and issues with smell. Can you taste? They are linked. Part of taste, part of enjoyment of food is smell and sight. So I would venture to say people who cannot smell can taste. They can taste. I know somebody who can't smell. He can taste. Favorite foods are things that are really spicy and really savory. Pizza. Okay? Pizza is one of his favorite foods. Textures. Needs stuff. He does not like foods that are all mush. Because the enjoyment of food comes not from the smell, it comes from the taste and the texture. So, yes, you can taste without smell, it just, the experience is not as great. Okay? So that's taste and smell. There is also skin senses and vestibular senses. Skin sense is the sense of touch. Well, when you touch, you have pressure, temperature, and pain. So I can know, for instance, if I have pressure on my hand, I can feel the pressure. I can feel the wind against my skin. Okay? I can feel that. I can feel the coolness of the breeze. So I can feel temperature, I can feel pressure, and we feel pain. There are a couple different things with pain. There is what's called the gate control theory. It's this idea of if our pain gets bad enough, then we have this mechanism in our body that helps to shut it down. That's why people can keep on going when they're in excruciating pain. And they say that they don't feel it as well. Because it's kind of like your body says, okay, I got the message, enough already. So that is kind of a gate control theory. There are also different types of pain in terms of there is the nagging, achy pain, and then there's the sharp pain. There's the pain that you get like when you pull a muscle and it just, like it's just a nagging. It's not really sharp. It's like a nagging pain. And then there's I cut myself or I burnt myself, like the real sharp pain. Those are different kinds of pain. There's also this idea of a small group of people that are born without the ability to feel pain. You would think that would be wonderful. You would think, oh my gosh, how good would it be not to feel pain? It's a problem because pain tells you if something's wrong, so pain can be good. You hurt yourself. You feel pain. Okay? You're cold. You feel cold, which tells you get a jacket on. That's a good thing. Pain tells you when you need to make adjustments. People who can't feel pain at all don't get that message. So they can get really sick and really hurt and not even know it. So that's touch. There's also the vestibular sense in terms of sense of balance. I can stand up here and I can go like this, and my sense of balance is telling me where I am in space and the fact that I'm turning this way and this way. Okay? That's kind of the kinesthetic and vestibular senses. It's knowing where you are in space, being able to keep yourself upright. In that, we have the eustachian tubes, which are right next to, believe it or not, are next, kind of a part of our ears. Eustachian tubes. And that's why sometimes when you get ear infections or sinus infections, you get a little dizzy. Okay, the last things, there's two last things, Gestalt principles. How do we see things? Okay? In other words, how do we, Gestalt is the whole is more than the sum of its parts. So how do we group things together? Well, we group things together by things like proximity. So if you look in front of me, there's a garden, and I see little plants coming up. Well, I can tell that I group a certain plants together because they're close to each other. So I can tell that they're the same. I group them together because they're next to each other. If you have groups setting in a stadium, and you have a group here and a group here, you're going to put these people together and these people together because they're in close proximity. Okay? We have similarity, continuity, and closure. Similarity is if you are at a sporting event, if you're at a football game and you see people wearing different colors, you're going to group the people in the same colors together. If you see, we went to a graduation. If you're at a graduation and you see a bunch of people in cap and gowns, you're going to group them together. Okay? Similarity. You're going to group people who are look-alike or dressed alike together. You're going to group objects that look alike together. In the garden, I'm going to group plants that look alike together. Continuity. I'm going to see rows of plants even though there might be spaces in it. If I were to draw a circle and leave little spaces, you'd still see a circle because of continuity. And the same thing with closure. Closure is we see the entire circle. Continuity is kind of if we see things that look like they're in a line, we're going to group them together. Closure is we purposely make that circle. We purposely finish it out. So those are Gestalt principles. The last thing, which is not which I wanted to talk about in sensation and perception, is what's called perceptual constancy. Okay, I'm going to get up again. And if you look, if I'm coming toward you, okay, the image on your retina is getting bigger. But you don't see me as getting bigger. You see me as staying the same size. That's an example of perceptual constancy. As something comes closer to you, the image actually gets bigger, but you see it as the same size. If I'm turning my hand, the image is changing, but you're not seeing anything different. You're still seeing a hand. That's perceptual constancy. Shape constancy, size constancy. If I were to go into a different light, if I were to go inside, things would be slightly different colors, but it wouldn't look like the color of my shirt changed. That's perceptual constancy. We see things as constant, even though the physical sensation might change. Okay. That's sensation and perception. I will see you next time, and we will talk about something different.